Hello and welcome back to episode 19 of Probability and Statistics for Engineers, and I am Mohammad Momenzadeh, the presenter of this lecture. So in this lecture we will discuss about many topics. We will have the quick review of a Poisson probability distribution, and we will give you one example of an approximation by Poisson distribution for the binomial distribution as well as we promised. And after that one we will recap all the type of the discrete distribution in one diagram, and we will give you one comprehensive example to have all type of the distribution in that example as well. And after that one, if we have fine time, we will discuss about the continuous probability distribution and uniform continuous distribution as well. So let us take a look at that example at the beginning of this lecture as well. Here we go. The example is given as follow. It is known that 5% of the book bound by a certain binary have defective binding. Find the probability that 2 of 100 books bound by this binary will have defective binding using the formula for the binomial distribution or the Poisson approximation to the binomial distribution. So at the question they mentioned about the type of the distribution that you should use, the binomial and also the Poisson. So but if it's not given at the question, even you can find and diagnose the type of the distribution. So it said that it's known that 5% of the book bound by a certain binary have a defective binding. Means that out of the probability of having defective binding for the book, if we consider a book over here, let us sketch one book over here. So if I have a book like this over here, then with the probability of 0.5 is 5%, so the probability of having defective binding is 0.05, so it's 5%, and the probability of having the good binding for that one is 0.95, and this probability is constant or invariant for the values of the for the books and for each cases that you have. It means that for the second book, for the third one, up to the end we have the same probability. So means that somehow we prepare the condition of the binomial distribution one by one. We have some trials, means that the trials over here is investigating about the quality of the binding of the book, and with the probability of 0.05, which determine the p or the probability of a success, it's going to be defective, and for the failure cases that the binding is good and well, the probability will be 0.95 or q is equal to 0.95. So out of 100 cases we have the number of material as well, so we have 100, so the number of the materials that we have it here is equal to 100. So out of 100 cases we want to know what is the probability of having two defective binary books for 100 cases that we have it. So if x denotes over here, if x denotes the number of defective binary books, so let me just write it over here, that what is a random variable as well, it denotes the number of successes, and the success over here is having defective binary. So by this actually random variable we can say that the x follow the binomial distribution with the given factors or characteristic that we have it over there. So x follow the binomial distribution with the n equal to 100, and the probability of success is equal to 0.05. Right now, if I want to calculate the probability of x equal to 2, simply you can use the binomial distribution function to calculate that one. Means that probability of x is equal to 2, means that we are looking for 2 success out of the 100 trials. I want to emphasize about the condition of the binomial distribution before that I go forward to solve the question. First, all these trials are independent. Second, the probability of success is not changed, it's constant for all cases, and it's not changed from one book to the another one. And a third one, the random variable x denotes the number of successes or having defective binary. So x is equal to 2, probability of x equal to 2 will be a combination or chosen of 2 cases out of 100 that we have it over there. So 2 out of 100 is a chosen of the combination over there, times the probability of a success over here, which is 0.05 square, because we have 2 cases of a success, we are looking for 2 cases of success, times 0.95 to the power of the failure cases, means that to have a well actually binary out of 100 cases where 2 are defective, so 98 remains over there. So this is the probability distribution function for the binomial cases. Right now, if I want to approximate that value by using the binomial Poisson distribution, then we should check something. First of all, the n number of n is 100, and it should be big. I mean, somehow it's tending to infinity, and the probability of p or success is 0.05. So in comparison, you can see that that one is too small, it should tending to 0, and the number of that trials is tending to infinity. And by knowing these two concepts, if we verify these two concepts, it's too small, the probability of success, and the number of the trials is too big, then we can calculate the expected value over here. The expected value of x is equal to np based on the definition of the expected value for the actually binomial distribution. So it will be 100 times 5 over 100, or 0.05. So if we multiply these two values, the result will be 5. So means that in an average we have 5 defective books over there. So right now we are looking for 2 defective books. So we can consider this one as a lambda t. Means that I can change the question like this. I can remove this part of the question to understand the concept of the Poisson distribution. We can remove this part of the question and said that based on an experiment, previous experiment, we realized that 5 books will be defective in a line of the production in one binary shop. So find the probability that 2 of the books will be defective in the next, a line of a production. So as you can see, it looks like a Poisson distribution right now. And with that information, we can solve the question as follow. Means that again, we can say that x is distributed as a Poisson distribution with the lambda t equal to 5. So I emphasize about the situation again over here, that we already changed the question somehow with the information that we have it in this case, like errors in the paper in the secretary's typing. In the cases that we have it over there, we have one value or one average things that is happened severally up to the end. So over here we change the question like this: if we have 5 defective actually binary in a production line, what is the probability to get 2 defective binary in a new actually line of the production? So right now we should use the Poisson distribution, and the probability of x equal to 2 in this case should be calculated by the Poisson distribution. And if you remember that, it will be e to the power of minus lambda t. Over here minus lambda t is minus 5, then lambda t to the power of x means that 5 squared over 2 squared, 2 factorial. So the result of this 1 can be calculated as follow, means that we can do that one over here. So if we just take a look, I put the solution over here and calculated the value of the binomial and Poisson distribution over here, and as you can see, the value over there is 0.084 for the Poisson, and for the binomial distribution is 0.081. Means that it's too close to each other. As much as the probability of the success is less tending to 0 and the number of trial tending to infinity, then this value will be more accurate indeed. So you can see what is the value of these 2 distribution based on our discussion. So in the next slide you can see the categorization of all distribution that we talk about it up to now. I just sketched a similar diagram in a class for the student to recap or gather all of this information in one diagram. As you can see, we have 2 possibilities for the random variable. Means that if you have a random variable, then it could be considered as a discrete, or it could be considered as a continuous random variable, and the probability distribution function for each of them are different. When we have a discrete random variable, means that they are finite or countably infinite cases, like a geometric distribution that we have infinite cases, like a Poisson distribution that we have the infinite cases. So in a case that is in a case that the discrete random variable is finite, so for sure it's discrete. But in an infinite case, you can find a gap between the random variables numbers. When we assign the numerical values, it totally can be distinguished the values of the random variable or the sample points that assigned by a numerical values. But at the continuous case, it's not the situation, and for sure the probability of one specific value for the continuous distribution function is equal to 0, and we should calculate the probability of one interval in a continuous random variable. However, for the discrete random variable, we discuss about the specific cases as well. In a discrete cases, we use a summation to calculate the expected value and the variance. For the continuous case, we use the integral to calculate the expected value and variances. So beyond of this being discrete or continuous random variable, we have several type of the distribution for the discrete cases. However, these cases could be more than this, but we list only the cases that we talk about it, and I encourage you to do the same thing for yourself. In this way, you can memorize it, you can categorize it in your mind better, and you can keep it in your mind the type of the distribution. The first type of the distribution that we talk about it was the uniform case. Over there we have a sample space that contains some elements x1 up to xk, and the random variable is occurring the specific case. And as you remember that the probability distribution function for that one was equal to 1 over k. So the probability distribution function, the f of xi at that case is equal to 1 over k. So by that probability distribution function, you can calculate the distribution function and construct the table of a distribution as well. The expected value, we calculated it as the same as a summation of that xi, summation of xi divided by x, and for the variances as well, we have the similar formula, and you can put one example for yourself over there to describe the situation for yourself. It's an important thing. When you just rewrite all these things, you can somehow review these topics and put all this information in one page. At the back of the page, you can put your example and write about your example. At the binomial distribution, which is our second discrete distribution, we discuss about several terrials. Each terrials are independent from another one, and each terrial can be considered as two cases. One is a success with the probability of P, the another one is a failure with the probability of Q, and these numbers are constant for each terrials. And the most important thing over here is the random variable, which determines the number of the successes, and the probability distribution function is given by this formula, and the expected value is NP, and the sigma square or variance is NPQ. An example of that one could be considered as a multiple choice question that we talked about it before. So the another type of the distribution that we talked about it before, it was the multinomial distribution. At the multinomial distribution, we have the similar thing like n terrials over there, with one difference is that each terrial can be splitted to several cases that we denote the events of them by E1, E2, E3 and so on. Means that instead of having two cases, two outcomes for each terrial, we have more than two cases. And over here x determine xi, indeed we have not only one actually a random variable, we have I random variable based on a number of the outcomes for each terrial. Determine the number of occurring of EI. So for that type of the cases, we calculate the probability distribution function by combination of x1 up to xn out of n. This is the combination cases of x1 up to xn out of n, multiplied by the probability of p1 to the power of x1 times to the probability of p2 to the x2 up to p k, for example, if you have k cases to the power of x k. So we discussed about that things, and we can consider the different nationality of the students in one classes as a one example of multinomial distribution that we talk about it already. We have talked about these things already in this class, and we determine that type of the question. So the another type of the distribution was the hypergeometric distribution, that we have a resource of two types. One type is our unfavor and another one is not. So the number of the objects over there was k, the another was n minus k, and we draw indeed the n objects out of this resource of an object. So the distribution function is given by this formula, and the expected value is equal to n times p, and the p over there was k over capital N, and we put the correction coefficient over here to calculate the variances of a given random variable. And of course x determine the number of type 1 or a favor in our drawn. So the another type of the distribution that we talk about, it was the geometric distribution, that the terrials and everything looks like a binomial, but the differences is about the random variable, which x determine the number of terrials, the location of terrials that the first success is done over there, has been done over there. So the another type of the distribution that we talk about, it was a Poisson Poisson distribution, that the time or a specific place or a specific time was important, and one actually average of them are given at the question, and based on that one we decided to use the Poisson distribution. So at this point I just try to make one example that cover all these type of 6 distribution that we talked about it before, and step by step we try to solve that one and talk about the differences of this distribution. As I said it before, when we talk about one type of the distribution, it's easy to realize that the example is related to that type of the distribution and solve it. But in an exam, in real life, when you want to talk about the distribution, one important thing is diagnosing the type of the distribution, and you can diagnose it based on a character of that distribution, which you can see it over here. I again want to emphasize about sketching of this diagram by yourself to just recap all this information in one diagram and keep it in your mind. So let us solve that example. The good part of the probability is about making the example. You can make an example by the happening in a day. I mean, it's easy to make an example. In each semester I just made the different questions to the student because it's too easy to make the question or create the new question based on a real happening or phenomenon in around of us. So let us take a look at that example. So I designed the example that cover all type of this distribution, and step by step I changed some concept in that example to have the different distribution. I started by the uniform distribution to see that how it's working. So assume that there is a classroom. I just use the concept that I have it in my hand and I just design it at the moment actually. So there is a class that contains 8 students, and we gave them a number. For each student I gave one number between 1 up to 8. Means that I just select one student by random and I give him number 1, 2, 3 up to giving number 8. And if we select one a specific student, means that we just select by a random one student from that classroom. So the question asks you that what is the probability of selecting the number 6, for example. What is the probability that we select the student with the number 6? So to calculate this probability we should learn something. We should just take a look at something that we have it over here, specifically about the number. So first of all, the probability of selecting each of the students are the same. Means that it doesn't matter that what is their number. We just select one student by random and we didn't care about their age, about their gender, or about any type of these things. And if X denotes the number of the student who is selected, so let us write it over here, denotes the random number that is given to the students of that classroom, then I'm looking for the probability of X equal to 6. Over here, because all the probability are uniformly divided by the student, the value of that one will be 1 over 8. Moreover, if I want to know that what is the average of the number that can be selected from the class, means that if I select one student, for example, the number of that student is 8. If I select the second time the student once, then the number is 4. The another one is 5. The another one is 2. What is the average of these numbers? Then I should calculate the expected value of X. That expected value of X is as the same as the average of that number. Means that you should add number 1 up to number 8. Number 1 is added by 2 up to 8 and divide by the number of the student that we have it over here. So means that it should be divided by 8 as well. So you can calculate that one. So the expected value over here is 4.5, means that in an average we expected to have 4.5 5 as a average of numbers that is coming out from that class. And sigma square, or the variance of a data over here, will be the subtraction of each elements. For example, 1 minus 4.5 from the expected value that we calculated before, square it and divide that number by the number of the elements that we have it over there. Means that the second one is 2 minus 4.5 square it and add them together up to the end. Means that the last one over there will be 8 minus 4.5, 8 minus 4.5 totally a square, and divide this expression by the number 8. So this will be the variances of this random variable indeed. So if we calculate the variance, it's going to be 5.25, and the roots of variance determine the standard deviation, which is 2.29. So over here you realize that when we have one specific elements of the objects or the resource that we have it over there, and we select one specific elements out of that objects, then you should use the uniform discrete distribution, and we calculate the expected value and the variance and a standard deviation for that case as well. Let us take a look at the second part and modify the question to have the binomial distribution over there. Again, in a previous example, we modified the question a bit to see that how the binomial distribution works. In the same classroom, we assume that there are 3 girls and 5 boys. Means that out of these 8 students, 3 of them are girls and 5 of them are boys. And we draw 3 students by replacement. This is important to mention that the replacement is allowed. Means that by replacement. Without replacement, then the situation totally will be changed. So the replacement is allowed, and let us put over here that the replacement is allowed. So means that the probability of being girl, for example, for the first student is 3/8, and for the second one also will be 3/8, and you may select the same student when you draw them from the class. It's too important to understand. It means that, for example, one specific person, I just consider number 5. Assume that the number 5 is a girl. I select that student and I take her out, and again I replace it back, and I could select the number 5 again. So this is the most important thing about the differences between the binomial and hypergeometry. Over here right now we have 3 trials, because we have the independent cases. Means that selected of the first student is totally independent from selecting of the second one, and is totally independent from selecting the third one. Moreover, for selecting of each student we have 2 cases. One of them is a failure, one of them is a success. And over here, for example, failure is being the boy in that type of the question that we have it, and the success is being girl in that selection. So right now the question is as follow: out of these 3 draws by replacement, what is the probability that exactly 2 students will be girl, will be female? So in this case we can denote the X as a number of the girls, number of the success over here, or number of the student, number of girls out of this actually draws, out of this class that we select 3 students from that one. So right now the probability of having 2 girls in that draws or selection means that probability of X equal to 2 will be equal to based on a probability distribution function 2 out of 3, because we have 3 selected at the beginning. The probability of being girl is 3/8 to the power of number of this selection, which is equal to 3, which is equal to 2. So we have 2 selection, and the probability of failure or being male is 5/8 to the power of number of these cases, which is 1. And if you want to know that out of these 3 students, out of these 3 selection, what is the probability, what is the average number of the girls inside of them, so you should calculate the expected value, which is equal to the number of n, or 3 times the probability of being girl, which is 3/8, means that approximately is equal to 1. It's 9/8 or 1.25. So we expected to have at least one girl out of these 3 selection from this class. And if you want to calculate the variance of x as well, the variance of x will be the expected value times q, or npq. So it will be the same thing that we have. It means that 3 times 3/8, and we should multiply that number also by the probability of being boy, which is 5/8, and you can calculate the variances by this method. So let us take a look at the multinomial now. So let us modify the example to have the multinomial distribution as well for that type of the situation that we had it before. So over here again we consider the class with 8 students, and right now we assume that 2 of the students are European, so I just denoted by E, and 3 students are from Asia, so we have the A alphabet for that one, and the remaining ones are from the other nationality, means that 3 from the other nationalities. So we just choose, let us choose 3 students, or select 3 students out of this classroom, and we want to have we want to have the different nationalities in these students, means that we want to have 1 Asian, 1 European, and 1 other nationality in this group of the students. So for this situation, as you can see, for each student, instead of having 2 cases, we have 3 cases, means that the student could be from Europe, could be from Asia, and could be from other nationalities, and the probability of each are different as well, and the replacement is happen as well. In this case we consider that the replacement is possible. So it's important to emphasize about this replacement, because otherwise you cannot solve it by the multinomial distribution. So in this case, because the probability of being European will be 2/8, 2 out of 8 students are European, the probability of being Asian is 3/8, and the probability of being from other nationality is 3/8 as well. So right now, to calculate this probability, we should denote the number of the European students by x1, and denote the x2 as a number of the Asian student, and the other nationality by x3. So that means we are looking for the probability of x1 equal to 1, and x2 equal to 1, and x3 equal to 1 as well. So with the total number of 3 students in a row that we have it, so x2 equal to 1 and x3 is equal to 1. So with that actually description of the question, we should calculate the given probability by using the combination of 1 1 1 out of 3, means that we have 1 1 1 out of 3 cases, and the corresponding probability to the given powers or exponent. So 2 to the power 2/8 to the power of 1, because we have 1 student from Europe, and 3/8 to the power of 1 again, we have 1 Asian student, and also the last one is 3/8 as well. So the result will be as follow, means that you can calculate it by 3 factorial over 1 factorial over 1 factorial over 1 factorial. So we have this expression for the combination part, and as you know, the 1 factorial is equal to 1, so we have 1 factorial, and at the end of the day we should multiply it by that terms as well, means that 2 times 3 times 3/8 cube. So this is the result for that case. As you can see, we have the formula of the multinomial distribution, and the remarkable example of that case is the nationality, as I mentioned over here. Let us do that, change the question to have the hypergeometric distribution. By some modification, we can have the cases for the hypergeometric distribution as well. So in this case, we modify the question a bit. Again, let us return back to the cases that we had 3 girls and 5 boys in the class, and we want to draw and make a committee of size 3, but this time we want to make a committee, and when we want to make a committee means that we cannot indeed replace the student, means that we cannot repeatedly choose one student from that class. And with that simple modification, the distribution is changed to the hypergeometric distribution. Means that right now I can divide this population to 2 parts. One part is a type 1, which is our favor, and the another one is a type 2, which is not in our favor. And to select, for example, to get 2 students from the male parts, let us x determine this random variable. Let's assume that the x denotes the number of girls in that or female in that committee, females in that committee. So in this case, we should calculate the distribution by using the hypergeometric distribution. For instance, if I want to have 2 students over here from the girls actually population, if x is equal to 2, to calculate that one, we should use the formula for the hypergeometric distribution. Right now we select 3 students out of 8, and also to calculate that cases, 2 students should be selected out of 3 possible students over there, and the remained one means that 1 student which is remained should be selected out of the boys or male students. So the result can be calculated right now by evaluating this expression. Moreover, you can calculate the expected value of x by the following formula. So the expected value over here will be n times p, and the n over here, the number of the selection is 3, and p over here is the number of the favored cases, which is 3 over 8. So this will be the number that you can find. This 9 over 8 means that we expected to have 1 girls out of approximately 1 girls in that 3 draws or selection or committee that we have it over there. And also you can calculate the sigma square or variance. So for calculating the sigma square, you should multiply n, which is 3, by the probability of favorite case or type 1, which is 3 over 8, times the probability of not favorite or the type 2 of the student, which is 5 over 8, and at the end you should multiply it by the correction coefficient. And the correction coefficient over here is the number of all cases minus n, or the selection part, over the n minus 1, means that 8 minus 1. So this will be the value for the variances, and you can calculate it in this case. So let us prepare the question for the geometric and Poisson distribution as well. So again, we have the similar classroom with the 8 students, and we add one more information in that question, that the probability of getting full mark in probability course is 0.4, means that for each student that value is constant and invariant from one student to the another one. So the question is about that if we select or giving the grade to the student, if the teacher reading their papers and trying to find the first full mark, what is the probability that the teacher gets in a third try the full mark in the papers. That means we have the exam for this classroom, and in that classroom we just gave them the question answer sheets, and the teacher tried to read the paper or mark the papers, and what is the probability to find the third try or third paper as a full mark. So this probability holds constant for all students. So in this case, as you can see, we are talking about the place of that happening, and this type of the distribution should be the geometric distribution. By the another word is x determine the number of a try or the location of a try. So let me just denote the location or a number of trying to get the first success, which is the first full mark over here in the exam. Then I'm looking for the probability of x equal to 3, because I want to get the first full mark at the third try of reading the paper. So over here, as you can see, it will be equal to the probability of not getting the full mark in 2 previous try. So 0.6 to the power of 2 will be the previous one, and the probability of the success or 0.3 should be multiplied by that value. So the expected value over here means that the number of a try that you should do to get the first full mark is 1 over p, and with that concept that we have it over here, which the probability over here is 0.4, so I should change it 0.4. I should correct this value to 0.4. I thought that is 0.7. So the probability of getting the first success over there, 1 over p, should be calculated, and it's 0.4, so it will be 10 over 4, and it will be 2 point something over there. So indeed, in a case that we have it is 2.5, means that between the second and the third try we expected to get the first success or the full mark. Means that the teacher in a third try for sure should get the first full mark of the grades over there. And the sigma square as well, the variances of the value for the for this random variable is equal to q over p square. So it will be q over p square, or you can replace q by 1 minus p as well. It can be happen. So the q over here is 0.6, and you should divide that value by 0.4 square. So it will be the standard the variances of this random variable, and you can see how can we use that type of the distribution to calculate these values. So let us take a look at the last example or the last part of this distribution as well. Right now again we return back to the classroom that we talk about it, and for this classroom we have one information that for each of these students, based on the previous information, we realize that each student, at least in their lifetime in the school, they fail one course in their life. I mean, in an average, the lambda t, or the possibility or the average of the time that they fail one course is equal to 1 time. And the question is as follows: if we select one student by random from this class, then what is the probability that the taken or selected student failed the course for 2 times in his life or her life? So actually this population should be considered that this study is done for all school, and it's gonna be happen in one specific time, and this specific time is their lifetime in the school. So right now this type of the distribution will be the Poisson distribution, and based on the definition for the probability distribution function, the f of 2 or failing the course 2 times in this manner will be equal to e to the power of -1, because the average is 1, and 1 to the power of x, or 1 to the power of 2, and over 2 factorial. So the result will be 1 over 2e, or 2 Euler number indeed. So it's going to be the value for the probability in this case. So as you can see, we just modify the question a bit, and for each case of this distribution we found one example of these cases. However, you can prepare some question with the different distribution that are not in this list as well. But for these 6 cases that we talk about it, we actually modify the question to find some type of the distribution for each case. So in an exam, most of the time we just gave the student one question that contains all of these distributions in once. So you should diagnose the type of the distribution, and based on the information that is given in the question, you should decide about the type of the distribution, and the solution in this case will be totally different. So as you can see over here, by just changing a word or phrase in the question or the situation of the happening or that statistical experiment, the question gonna be changed totally. So you should care about this situation, and I hope that you understand the differences between this distribution, and also realize the differences and distinguishable part of this discussion. So in the next lecture we will discuss about the different type of the distribution function for the continuous random variable. So I will finish the lecture at this point, and thank you for your attending.